Hi everyone, it's Crystal Cullum, and today I'm going to talk about generating acetyl coenzyme A into pyruvate. This process is a step in the link between glycolysis and the citric acid cycle. Here, glucose undergoes an irreversible conversion through glycolysis to become 2-pyruvate, which is subsequently converted to acetyl coenzyme A. There are basically 3 steps in this process that we'll break down further. The first being decarboxylation, then oxidation, and finally the formation of acetyl coenzyme A. This image is of a basic cell. Highlighted is the nucleus, the cytoplasm, and then the mitochondria. Glycolysis takes place in cytoplasm, and the citric acid cycle takes place in the mitochondria. In the middle of the mitochondria is the matrix, the center, which is protected by layered membranes, which are folded on top of each other. So ultimately, we want to get our enzymes into the matrix of the mitochondria so that cellular respiration can complete. So, as we talked about earlier, glucose will undergo glycolysis and generate the 2-pyruvate, which are then converted. Each pyruvate has 3 carbon molecules, and when the pyruvate loses a carbon molecule, what we have left is the acetyl, which just has the 2 carbons. Every time a carbon is lost, it is lost as CO2. On this slide, we can see in box labeled 1, the pyruvate, and it's showing what carbon is being removed. As this is being removed, it's being removed as carbon dioxide, so we broke this bond here, and that's going to leave some electrons available for us to capture and for us to use for further cellular respiration. However, we cannot capture, we can't just reach out and grab these, because at this point it's a free radical and that can be dangerous. So it needs something to bind to. So as you can see in the second one, we are going to show how we take it from where it's dangerous and that free radical and make it into something more useful. So the molecule we're going to use here is NAD. When we add the molecule to NAD, it becomes NADH. Then in the third box here, we can see an acetyl group being transferred to a coenzyme A, resulting in acetyl coenzyme A. This image allows for a more flow type diagram to kind of explain how the pyruvate loses the CO2 and picks up NAD to handle those free radicals, and the CO2 binds to that, and we get the acetyl down there from that loss of that first CO2, and that combines with the coenzyme A and gives us our final product of acetyl CoA. So really, acetyl is the enzyme trigger that is needed to move on to the next step. But as we talked about earlier with the mitochondria, it can't just directly go into the mitochondria because it's protected by the membrane, which is only semi-permeable. So we utilize coenzyme A as a ticket to get in to the membrane, to get through the membrane. The coenzyme A binds to the acetyl and forms that acetyl coenzyme A, which is accepted into the mitochondria. So now that it's converted, it can travel through both layers and carry on into the matrix. At that point, when it's in the matrix, the coenzyme A can just leave because it's no longer warranted. So it leaves just the acetyl behind, and then the citric acid cycle can begin. These steps are all carried out by pyruvate dehydrogenase, which has 3 interconnected enzymes and about 60 subunits. This complex regulates the amount of acetyl coenzyme A that can actually be fed into the citric acid cycle. I think that this picture does a good job of showing how the whole process is continual, with pyruvate being a key factor. The pyruvate can be made from the glucose through glycolysis and then be converted back into carbohydrates such as glucose via gluconeogenesis, or to fatty acids through the reaction with acetyl coenzyme A. Thanks for watching my slides, and hopefully I explained it in a way that is easier to understand.